Hello, we're Team Beta, and we were asked to train and test the best machine learning model to predict customer churn. To do this, we'll prepare our data for processing and then compare multiple machine learning classifier performances based off of their awk score. Looking at our data, we can see that we will be using various customer attributes, such as demographics, subscription details, and billing information. We have also been provided a label for whether a customer churned or not, which will be our prediction target. With our Python libraries imported, we can find more in-depth details, including row count, column count, and if there are any null entries in our dataset. Since no invalid entries are detected, we can move on to data preprocessing. One thing that we did see in our data was that total charges was not being stored as a numeric column. When we searched for non-numeric data in the column, we found 8 entries that cannot be counted. To fix this, we can convert the actual numeric data to the correct data type, and then we can replace any object data types with the most frequent category in the column. Additionally, we will replace any null data that is found with the column average. With this finished, we can see that total charges no longer has any issues. With our data cleaned, we can move to feature selection. We can remove the ID column as it will be irrelevant to our testing. We also separate our target variable label to be used later. We can see the distribution of our data by graphing each numerical feature out. In doing this, we can see that tenure is almost completely uniform, and we can see that total charges is skewed heavily to one side. For the rest of our data, we can use one-hot encoding to convert all categorical data to values of ones and zeros. This is so that the data can be understood by our models. We can then check for collinearity or any data pair that is highly correlated and can be removed for redundancy. We can see this easily through the use of a heat map. After removing highly collinear features, we are left with 33 out of 45 columns. We can also check for multicollinearity, or when multiple features are highly correlated with each other. Using the variance inflation factor to detect multicollinearity, we can reduce our features to just 2 columns. With our features selected, it is also a good idea to consider our target variable label balance. This is due to the possibility of our models learning a bias towards a majority class, which can be misleading. In testing this, we can see that our labels consist of only ones and zeros, with zeros appearing approximately 2.7 times more than ones. We'll keep this in mind if we need to optimize our data further. With all of that done, we can finally split our data. We'll be using a 70-30 split, which will allow for a majority of the data to be used for training and the rest of our data for unbiased validation. It should be noted that the split is randomized to ensure data positions do not affect our training. Finally, we will standardize our numerical data, ensuring that all data is represented equally and our models behave as expected.
After data exploration and pre-processing, we move on to the next section, model training and evaluation. This section trains and evaluates 7 machine learning models on the training data set and then assesses their performance on the validation data set. The get metrics is a function that takes input as test labels, prediction probabilities, and then calculates and returns the performance metrics such as AUC, ROC scores, accuracy, precision, recall, F1, along with TPR, true positive rate, FPR, false positive rate, and the confusion matrices for various models. Next, we are training various models using the fit methods, predicting the probabilities and the labels using the predict methods. Predict and predict proba methods. We calculate all the performance metrics which can be used to plot AUC ROC curves as well as to evaluate their performance. The table shows logistic regression scored a high AUC ROC score of 83.01%. The receiver operating characteristic curve is a graph that illustrates the trade-off between the true positive rate and the false positive rate at different classification thresholds. Here we plotted AUC ROC curves for different models. The diagonal of the ROC graph can be interpreted as a random guessing, and classification models that fall below the diagonal are considered as worse than random guessing. A perfect classifier as an AUC has 1 and would fall into the top left corner of the graph with a TPR of 1 and an FPR of 0. A random classifier has AUC as 0.5 and a worst classifier has an AUC less than 0.5. At this graph, I would like to mention at first we used calibrated classifier CV for perceptron and SGD. The calibration is often applied to models where predicted probabilities do not match the true likelihood of outcomes. The calibration process is typically used to improve the reliability of the probability estimates. However, the calibration process gave a discrepancy between the AUC score and the curves for perceptron and SGD classifiers. So calibration has been removed on these classifiers and replotted. This time the curves and the AUC scores matched perfectly. Next, we move on to the model evaluation of the 5 models: logistic regression, random classifier, stochastic gradient descent, and the boosting classifiers such as XGBoost and LGBoost using hyperparameter tuning. Each classifier has been evaluated twice, once using the grid search CV and second time using SMOT and grid search. And each model calls the train predict method, which uses the grid search CV, which evaluates all the hyperparameter combinations exhaustively, ensuring the best combination is always found. The grid search CV also uses k-fold validation for comparing models trained with different hyperparameter settings. In k-fold cross-validation, we randomly split the training data set into k-folds without replacement. Here the k-fold or CV is set to 5. So four folds, the so-called training folds, are used for model training, and 1 fold, which is called the test fold, is used for performance evaluation. The procedure is repeated 5 times so that we can obtain 5 models and performance estimates. We then calculate the average performance of the models based on different independent test folds to obtain a performance estimate that is less sensitive to subpartitioning of the training data compared to the holdout method. In all these methods, in all these models, to address the imbalanced class labels, the 2 techniques are employed. One is the hyperparameter class weight is set to balanced instead of none or uniform. And the second technique is using SMOT. The SMOT is called synthetic minority oversampling technique algorithm, which is used to generate synthetic samples for the minority class. The parameter sampling strategy is set to minority, so that only minority class is oversampled until it reaches the number of samples in the majority class. After evaluating all the 5 models, their performance metrics are calculated and they are tabulated as follows in the form of a table. Here this table shows the AUC RSA scores after hyperparameter tuning of all the different models. And this is the receiver operating characteristic plots for the different models. From the plot, we can see that the logistic regression, LGBoost, random forest has the highest AUC score of 0.83, followed by SGD with a score of 0.82. The dashed line shows the score of 0.5.
Hello, my name is Nicholas Brown Duncan, and I will be performing the 3rd section of this presentation. I would like to start us off with confusion matrix for our models after we perform hyperparameter search. As you can see in this confusion matrix, our logistic regression model had the highest true positive score of 899, though it also had the highest false negative score of 105, whereas XGBoost had the lowest true positive score of 642 with the lowest false negative score of 57. We believe this is the case due to the logistic regression feature favoring outliers which are closer to its boundary lines, whereas XGBoost is a bit more conservative in its label guessing. And these are observations we made about the confusion matrix in general, though for the sake of time, I will leave it for the viewer to read. And after performing the computer matrix, we decided to create a voting classifier model. What the voting classifier does is it combines the best of two models and tries to mitigate the worst of both. So in our case, we combined logistic regression with LG boost, as they were the top two scoring, and our confusion matrix with LG boost having the third best or third worst false negative score. In this case, you can see that it created a AUC-RC score of 83.2%, whereas when compared to other models, it marginally beats logistic regression LG boost by itself, all three of which beat Tyrannosaurus and SGD, and all of which beats XG boost. And so due to this, we decided to select voting, logistic regression, and LG boost as our models, as while voting had the highest score, it only marginally beat logistic regression LG boost by a factor of 0.2%. And then we would like to point out a couple of challenges we had with this data set. So first of all, the data set was pretty small, which made it hard for our models to learn meaningful patterns or generalize to unseen data. There was a strong class imbalance where Churn has had significantly fewer recordings than the majority class of non-Churn. We're able to mitigate this by using SMOTE to oversample the minority class, but it's something we like to point out. In addition, there was mixed data types, so this training and testing data had a combination of categorical and numerical columns, which we were able to mitigate by using one-hot encoding. And then, as you know, with the curse eventuality, this data set had many features. We recorded up 19 features prior to one-hot encoding. I believe it was 43 features after one-hot encoding. And so we noticed that the dimensionality reduction became very important just to make sure our model were able to train in a reasonable amount of time. And then for data quality, overfitting, and probability calibration, I'll leave that to the viewer to read. And then we would like to point out some of the strengths and weaknesses of all of our models. So voting classifier it's great because it's able to leverage the strength of multiple classifiers, but as you may know, it is computationally expensive. So when you are dealing with a large data set, it takes a very long time to properly train these types of models. Luckily, on our case, as we mentioned previously, we were only dealing with smaller data sets, so we did not have to worry about this limitation. And logistic regression works well for features in which you can draw a clear linear line between labels, which most of our features did fall into. For the rest, I will leave it to the viewer to read, as we are running a bit short on time. And then in this section, we just performed training on a full data set. As mentioned previously, we trained logistic regression, LG boost, and voting classifier. And in this section, we performed data pre-processing. While there was no NaN or invalid data sets in the test data sets, once we converted the total charges data set from a string to a float, some of the rows became NaN due to them previously being an empty string, and this is just to standardize against that. And then lastly, we performed the actual predictions. So in this section, we're making voting classifier. In this section, logistic regression, and in this section, LG boost. And lastly, just some observations we like to point out. As mentioned previously, there was 19 features prior to one-hot encoding, 45 features after one-hot encoding. There were strong correlations between our features, and we found that after one-hot encoding, we could drop down to 33 features. There was a strong variance inflection factor for a majority of our features, and after scoring them, we noticed that only 2 of them had a low enough variance inflection factor that we wanted to keep. We attempted to create new columns as we noticed the strong correlation between features, but because of that strong correlation, we also noticed that these columns didn't perform any meaningful work for our models, so we ended up dropping them. And then, as we discussed, one-hot encoding versus label encoding, we noticed the difference was minimal, if any. The difference could be attributed to the random seed being different, could be contributed to label, but they were so minimal that we believe that whether we use one-hot or label, it would have been the same. And for the rest of these, I will leave to the viewer to read, as we are running short on time. And lastly, just as we mentioned, we trained voting, logistic, and LG boost. For Kaggle, the final submission with the highest score was voting, though we did perform multiple submissions with each of these models just to try to see if we could optimize better. And then the ROC score for voting classifier, once we submitted it on the testing data set, was 85.9%. I'm Nicholas Brown Duncan, and I thank you for listening to our presentation.